Thanks for the invitation here. My company is Dhruva Space. We are India's first small satellite company and high altitude ballooning company. I'll just give some introduction of the company itself a little bit and then talk about Arduinos and so on. So basically, me and my partner who started the company, Sanjay, we both were classmates in Europe. So I've studied in Germany, Sweden, and France before. And worked with the German Space Agency, DLR, for a wee bit. And then I returned back to India to start the company, Dhruva Space, along with my colleague. So we've had experiences in US, Europe, Singapore, and many other countries before starting the company. And within our team members, we have worked on 3 particular missions. So Sanjay, my colleague, has worked on the SRM-SAT mission, which is a University Small Satellite mission from India. And he's also, we're also part of the Singapore mission called VeloxP. It's a small satellite from Singapore, launched, I don't know, about 6 months ago or something like that. And so we also have Divya here, who is a part of the StudsSat team, which is India's first Pico satellite. So generally, we are into this new space era where we are trying to privatize a lot of markets here in India with respect to space, at least. So just as an introduction, our vision is to privately design, operate, and command private satellites here from India. So these are for Earth observation solutions for different market segments, as well as C4ISR, which is military-based solutions, and so on. So we are also exploring data downlink services from the Indian subcontinent. That means that satellites from many other countries can actually downlink the data over India, which is not really done right now, because ISRO is the only player around here. So we have a couple of strategic partners. One of our partners is in Berlin, and the other one is a university down south, which is building a 15-kilogram satellite right now. And we are trying to provide them some engineering support and solutions for this. So this is a brief introduction. And so how many of you guys have heard about anything about CubeSats? Anybody know what's a CubeSat? Yeah?
No, I just heard about it.
Okay. So I'm going to, in the next few graphs, I'm going to tell you what really is happening in the satellite industry per se. Whenever people talk about satellites, they think about these big ISRO rockets that are 300 ton or whatever it is, and then these 1,000-kilogram satellites that takes the size of this room and so on. But satellites can be really small. They can be as small as your cell phone or even smaller. So anything, by definition, anything that is orbiting is a satellite. So it doesn't mean that a satellite is the size of its room or something like that. It can still be something small which is orbiting. So, but people don't go by that convention traditionally. So this is just some more that we are trying to explore on video capabilities directly from space. If a few have seen one of these movies, Any Be Behind Lines or Any Be Behind the Gates or something, where they're directly relaying satellite video, behind enemy lines. So where there's directly relaying satellite video. So that is something that is possible, but it's still not, the technology is still not there yet, but that's where we are moving towards, where you can directly relay video capabilities from space and so on. So that's where the industry is moving. So we're also exploring encrypted downlinks and leasing satellites and so on. So, but this is a view graph that is more, per se, generic, where I would say, if you look at the evolution of the satellites and the smartphone industry, it's something very similar. So we had these huge computers in the 60s and so on, where you could, the word booting came from actually kicking the computer and starting it. So, and then you had the PC revolution coming in, and then you had the smartphone revolution, the laptop revolution coming in, and then now you have all kinds of smartphones there. So this has taken, it's traditionally Moore's law, which is very evident there. But then this is really applicable to satellites themselves. Because conventionally, satellites were built small, because you didn't have the rockets to take them so far up. But then as you become power hungry, you build bigger rockets and you want bigger satellites and so on. So, but then now people are coming back to a lot of small satellites because technology is miniaturized and a lot of things can be explored. Although space is a very harsh environment per se, but then people have experimented with industrial grade equipment in space. So why I say industrial grade is because Arduino per se can be said as for industrial applications. So that's why I come to that point. So if you look at some of these satellites, so this is just a mock-up model. So this is actually a 1:1 model of what can be flown in space. So people actually have flown this. About 200 of them or more are in space right now. The exact site, 1:1 of this. And it has a lot of capabilities in it. So here we actually have a camera there, which could actually take some pictures. But then you can do all sorts of science experiments. You can do a lot of communication experiments and so on. So if someone of you is a ham, for example, amateur radio activists, a lot of them use these kinds of small satellites to establish their communication networks. And when there is no real, when there's a big disaster, the only sort of communication that there is ham communication that can be done over satellites or ground systems. So traditionally, if you look at smartphone evolution, somebody like Google came up with Android, and it became a platform for developers. So people used it for a lot of things. So there's cloud computing, there is texting, there's voice calls, there's video calls, maps, so many other things. So traditionally, we are looking at, in the CubeSat domain at least, people are looking at how can all of this be done by this. So in the near future, you can already see that internet from space is going to be a reality. You don't need ground-based networks. There's already a company in the US which has a geostationary satellite which is providing direct 20 Mbps internet connection over land via space. So all of these is the next generation. So this is some of the things that we have actually had experience building or working with. So this is a normal dish antenna which can support downlinking of satellites and so on, and others also, but not. So more towards the theme of this topic here is a lot of high altitude ballooning. I'm going to speak more about this and show you some videos in the next few slides. So this is something unconventional because once we did an experiment in Sweden, in the Arctic, in Kiruna. So if some of you guys know Kiruna, it's one of the extreme places to live in. Temperatures fall up to about minus 45 degrees during winter. There's no sunlight for about 6 weeks, and there's totally sun for 6 weeks because it's just in the North Pole. So it's one of the great places to study auroras. If you know, it's northern lights. So we were there studying auroras and so many other things. So there we got experienced in doing these high-altitude ballooning flights, where you could actually launch these balloons, low-cost balloons, to do a lot of science. So traditionally, there's a balloon, and then these balloons reach up to about 35 or 40 kilometers. So you can actually do a lot of science or engineering with it. And then for example, if you want to study your clouds, the clouds are at about 10 kilometers. So you just reach the clouds and do whatever studies you want. And then you cut off the balloon and you recover your payload. So there's a cutoff mechanism that is shown here. And then you have a parachute that carries back the payload itself. And then you have the payload and then a tracker box. So once we came in and started our company here, interestingly, we had a client, Indian Institute of Astrophysics, which was trying to explore low-cost ballooning, low-cost astronomy itself. And they thought, okay, why not choose ballooning for this? So traditionally, it's because there's a difference between satellites and ballooning. So any of you have an idea of how much 1 kilogram of this to space, delivery of just 1 kilogram of this, not the material cost of this, delivery of just 1 kilogram of this into space costs? Any rough idea? $20,000? So that's about the Indian cost, which is around the cheapest around the market. So in the US, it's about $100,000. So one kilogram of this cost me 65 lakh rupees. So if I have to send this into space. So that's the cost in space. So traditionally, you don't talk about numbers of thousands and hundreds in space at all. If you're talking in space in terms of satellites and other things, you only talk in millions. So if you have to do science like that, it costs you a lot of money. So traditionally, this sort of ballooning helps a lot of people do a lot of observation of the upper atmosphere and so on in the stratospheric levels, at least conventionally using this, because that balloon costs you maybe 3,000 rupees. The gas there costs you about 10,000 or 20,000 rupees. And then it's just the hardware itself as to what you build and how cheaply you build. So we came up with this solution of actually using Arduinos for a lot of different things there. So for example, the cutoff mechanism which we had to build was Arduino based. And we had to actually track the package, right? So it's not that you just fly the package away and you lose all the equipment, because some of the equipment is really expensive. So for example, if you're flying a spectrometer of some kind, it costs you maybe 5 lakh rupees. Yes, it's of course cheaper than what you invest in space, but then it is really expensive for Indian terms. So we had to come up with a good solution to actually track down this package and bring it back to us. So then we came up with this nice idea of making a tracking package which is independent of the development of a payload by a scientist, because ultimately the scientist is interested in science. He's not interested in how you bring back his balloon or how you give him the data. He's ultimately interested in the data itself. So we came up with this idea that the scientist builds actually this, and he forgets everything else, because other things are not really related to his science. It's just the way to get his science done. So we came up with this solution, and we said, okay, we're going to provide you this, only you need to build this. And they were really excited for this, because that would make them really independent in their development, and the development cycle itself takes a lot less time, and the engineering of it takes a lot less time as well. So basically, this tracking package there, it's all commercial off-the-shelf equipment. So if some of you guys know, the Arduino-based tracking devices are also available. So there's one which uses APRS. If some of you guys know APRS, it is Automatic Packet Reporting System. So it's actually, you can report your GPS location via packet radio. And Arduino has a Tracuno board, which is actually used for this. So you can actually use this board and transmit your GPS location. And as a redundant system, we found that we cannot just use one thing. So we had to do something more as a redundant system so that we don't lose the package itself. So what we did is we chose to use a GSM-based tracker, also based on Arduino. So what that happens is even if you lose the package somewhere at 30 or 35 kilometers, if it's not transmitting, of course the cutoff mechanism is timer-based, so it would just cut off and it brings back the balloon. And then once you are at below 5 kilometer range, your GSM network just works, because GSM network works up to about 5 kilometers. So then your Arduino-based GSM GPS transmitter would work and send back the coordinates over cell phone. So you could just press a button on your smartphone and it gives you a location and just drive with this coordinates of that. So that's what we did, and we just additionally added a GoPro camera just so that you can get really beautiful images of the Earth horizon. So this has become like a really hit, at least in the scientific community who are doing a lot of ballooning. We've had inquiries from Dubai and UK for these things, and so generally this is like one of the packages that we offer now for scientists. So just other things that we do, we supported a lot of universities in becoming their FEST partners and other things where we bring them into the space platform and see what they can do. We also organize this Space Up, which is an unconference. It's a space-based unconference where it is like a maker festival for space and so on. The last time around, what I did is just by an interest, I thought, why not fly the Nokia phone on our balloon and see if I can actually record video and if my phone survives. It's a 3,000 rupee phone. So I just wanted to test how good the hardware is. And it actually recorded the video, and it was really functioning well. And even after the recovery, it really functioned well. So it went to about 27, 28 kilometers, and the phone survived. So it really shows that, and you can tell because at 20 kilometers, your atmospheric temperature is about minus 80 degrees. So if you can say that your Nokia phone, which is 3,000 rupees, is built to survive that, a lot of things can survive space. So it's just that the fear factor of space itself, or the awe itself, makes it difficult. So here's a bunch of students who actually built a satellite using a Google Nexus and had an Arduino monitoring the cell phone itself. So
PhoneSat is a project currently at NASA Ames, and the goal of the project is to make a CubeSat, which is a very small satellite that uses a cell phone as its central processing unit. So we use a Nexus 1 because the Android operating system runs on the phone, and it tends to be very easy to sort of hack in different kinds of ways to achieve the results that we're looking for in the system. So in addition to the cell phone, we also have an Arduino processor on board that actually watches the cell phone output to make sure that the cell phone is still running. So you may know that your cell phone might crash every once in a while. We have a system on board to make sure that that doesn't kill the satellite. So the goal at the moment is to sort of prove that cell phones can actually work in space and be used as the central processing units of satellites. So most of the sensors that we have on board are used to actually monitor the condition of the cell phone and make sure that it's working properly.
In my guess, in my experience, I think there are already about 10 satellites, more or less, that are using Arduino-based or even more based processing, or an Arduino-based onboard computer that is flying in space right now, and a lot of them are functioning really well. So this is one other example from the UK. So it's basically one of these small CubeSats. So this is a 3U1. That means three of them stacked on one another. So which is actually measuring the electron density, and this also uses an Arduino inside. So coming to the other big project, any of you guys know about Kickstarter? Yeah? Okay, so NanoSatisfy, who's one of our US partners, was a Kickstarter-based company. So these guys were students at the International Space University. We know them by persons and so on. So they came up with this freaky idea that why not raise money for a satellite on Kickstarter out of all the things. So generally that was like not the idea to go with traditionally at that point of time on Kickstarter. But these bunch of people said, why not do that? And then they wanted like $50,000 or something like that to build this first satellite, which is based on the Arduino itself. And then they just went online and then did the Kickstarter video and then put it up. And it was amazingly, they got the money in 16 hours or something like that. So it was one of the most successful Kickstarter campaigns. So they came up with this idea of making the world's first open source satellite, where public can actually log on to the satellite and use it to do experiments by themselves. So the ArduSat itself is, the initial ArduSat itself was the same size, 10 centimeter cube, exact dimension. And it was actually thrown out of the International Space Station. So right now there are about 3 satellites, the ArduSat, and they're adding about 20 more satellites to this, all based on Arduino. And all of them probably will be launched from the International Space Station. So it's really like the International Space Station now has a robot arm on the Japanese side, and all these satellites, small satellites, are stacked in there and then just thrown out of the Japanese arm. So most of these satellites survive there for about 6 months to do these experiments, and then they just return back. So this here, I think, is the world's most powerful Arduino board because it has 16 Arduino Uno all stacked in one board. And it has one monitor, which is actually multiplexing 16 things together. And so you can, what the aim of this is that you can run 16 experiments on a satellite at the same time. So there are 25 sensors on this satellite. Some of them basic sensors like temperature sensors or radiation counters and so on, and some advanced sensors like a camera or a spectrometer and so on. So the idea is you can actually log on to the satellite, and it's mostly used in for STEM education. It's been really popular in the US. STEM education is really picking up. So I mean, even NASA has promoted this for this reason. And this strange company, which we thought was not going to do so well or so on, but then they're really successful. So they went from raising $50,000 on CubeSat on the Kickstarter campaign to getting VC funded to about $3.5 million right now. So they will come up with a full constellation and so on. So that there you can really run quite a lot of experiments. I think it's scheduled to run like 5,000 experiments or something like that every week or something like this. Yeah. So basically, this is more like the layout of it. So initially, the first was an experimental satellite, I think, and then now they have like the 3U design. That's more the first one. Then the next ones were actually three of them stacked together. So these are different parts of the satellite themselves. So how you run this is very simple. So what they've come up with is an online portal. So anybody who wants to get into this, they need to subscribe. It's something like $125 for experimenting 3 days on this satellite, complete days. So which is actually, I think, the lowest in the market. Nobody can offer such prices. But then, you log on to their website, and they actually show this for a really novice user. So they can actually start knowing how to actually work with Arduinos and how to actually work with small temperature sensors, and then you move along to work with better sensors and so on. And then, so you can actually upload the code to the satellite itself. So there's a platform where you can run your code, and there's a test bench in San Francisco where your code runs through, and it gives you a verification that your code is working and needs to be uploaded to the satellite, so that the satellite doesn't do something mad, so that your code is bad. So there's a test bench that runs through, and then you get to the satellite. It's scheduled on the satellite then, and then the workflow happens, and the satellite runs the experiment, and then you get back the data and so on. So there's also a possibility of designing your own sensors for this. There was a campaign, I think, that they put up where people could actually design their own sensors, and they could actually fly this on the RDSat and give you the data and so on. So some ways of making more creativity, I would say. But then I think they're also looking at, with this, it's not just education or outreach. Constellation of satellites gives you a lot of power because it's the data that gives you power. It's the analytics that gives you power. So if you have 20 of them or 25 of them orbiting the Earth, then you have images of all kinds. You have data in a timely manner of all different kinds. So it can be used for a lot more science, a lot more industrial applications. And that's where I think there's a lot of application there. So this is one more example with respect to space. So moving along from Arduino, this company was, again, I think also Kickstarter based, maybe. My Spectral. So this is a spectrometer. If you guys know ocean optics or something like that, any spectrometer would not cost you more than $2,000, $3,000. Even if it's industrial grade, if you want to use in medical imaging or whatever it is. So these guys came with a Spectrino, Arduino-based spectrometer, and I think it cost something like $200 or less than that, something like. So which is really 1/10 or 1/15 the price of what is there in the market. So this was actually flown on the ArduSat as a payload to see if Spectrino actually works in space. So they've been getting results. So this is another such platform which is based on the Arduino. This is called ArduLab. It's by a company called Infinity Aerospace in the US. So what happened is in the International Space Station, there was a company that came up and said, we want to commercialize some parts of the International Space Station so that we get revenue out of it. And so they came up with this idea of giving universities, many other people who are interested to build experiments in a small place in the International Space Station where astronauts can experiment those things and give them the data back. So this company came up with this idea that we will give you space of so much, 1 liter space, 10 by 10 by 10 centimeter space. And in this 1 liter space, we'll give you so much power, so much time, so that you can experiment. And so you can build this experiment for this size, and we will put it on the International Space Station, and you will get your data back. So a lot of people signed up for it. It's one of the most successful space companies right now. And this company went with a collaboration with them and said, we're going to build an Arduino-based system where people can just plug in their experiment using the processor there and run their experiments on the International Space Station. So this thing costs about, I think, $1,500 or $2,000 in the market right now. And it's ready for space, so you can directly buy this off the shelf and put your experiment there and give it to nanoracks, and they give it to NASA, and they fly the experiment on the International Space Station. So this is one of the space experiment platforms based on the Arduino itself. Coming back to ballooning, so this is some more images from our balloon platform. So as I said, you can see the Arduino-based GSM tracker there. This is the cutoff mechanism. One of the shots from the balloon at about 15 kilometers. So the real trick while dealing with Arduinos or anything is that how nicely you can package it for it to survive in space, because that is a great challenge. You can use the processing and then the code and so many other things, yes, by themselves. But then how to make it really survive space in such an extreme environment is where the challenge is and where the IP lies when it comes to using Arduinos in space. So one of the tricks in high altitude ballooning may be to use really good packaging, as in we use military grade packaging where you can make sure that it really doesn't get affected by temperature. So even though the outside temperature is about minus 80 degrees, our board it never goes below 0 degrees ever. So we have tested one time where our board was, the balloon was hanging in at about 20 kilometers for 12 hours continuously. So imagine being in minus 80 degrees for 12 hours, and our board never left, it went below minus 2 degrees. So, and that the Arduino can still take. So if you're operating at minus 80, of course, nothing can survive. So it's really as to how you deal or how you come up with a nice engineering solution to making this work. So this is just a part of our kind of outreach activity where we show people when they invite us to schools and universities as to how things work with Arduino. So this has an Arduino inside with an inertial measurement unit along with it. So one of our team members has actually programmed it to show people how actually the attitude sensors are used on satellites to see how it's oriented in space and so on. So I want to show you two videos.
With the ArduSat Control Center, users get access to a suite of simple and accessible tools to get started very quickly. That includes a view of where the satellites are located, the user's active projects, and links to development and learning. On the learning side, users receive an online video course with varying levels of difficulty. A novice user can easily watch a video that introduces them to simple concepts, then take a quiz to test their knowledge. Sample code referenced in the videos easily gets a novice user started. After watching a video, the user can move over to the Development Center and begin building their first Arduino application. A common first application is a simple example that blinks an LED on the Arduino every 1000 milliseconds. A user with an Arduino can plug it into the computer and click a button to upload it right to the connected unit from their web browser. They can make changes, re-upload, and get immediate feedback on what they changed, like reducing a delay and flashing the LED faster. A more advanced user can jump right into an example for how to use a particular sensor, like a Geiger counter or a magnetometer. Just like the novice user, sample code is available. Even if a user doesn't physically have the sensor they want to use, they can still verify their code and submit it to our satellite workflow. That process includes testing and the actual upload to the satellite. Once the application has been submitted, a user sees the status of their application in the Control Center. Once the application has been accepted, uploaded to the satellite, and run, the generated data is available to download in a widely used format. The data can then be used in spreadsheets, presentations, artistic visualizations, and more.
So this is just one of the videos from the balloon experiment itself. So you can see. So yeah, as I was saying, the entire package was about 6 kilograms or something like that. And so we just filled the balloon with helium. So there's a lot of difference again here and the other ones. So this balloon there in Sweden costs maybe like 2 lakh Indian rupees to make just the balloon itself. But then the ones we are using in India cost like 3,000 or 4,000 rupees. So the material of the balloon, the making all makes a difference. But then if you want to do really low cost, you can actually do it. So It's not really beyond hobbyists and amateurs to actually do such things. Yeah, we had like 2 GoPros looking forward and down so that we can get some video and so on. So there was actually a cloud measurement experiment where the ice crystals in the cloud would actually come inside, and there was actually an imager below where you could actually image the crystals in the cloud itself, and then yeah. So just to give you more about the applications of such things, sometimes the way we use technology can be different for different applications. So there's always a lot of confusion in users as to what to use UAVs or satellites or aircrafts or balloons and so on. So all of them are really different segments, and all of them have their own advantages and disadvantages. So, but then if you use one of the great applications on a balloon platform is that you can actually tether it with a power line at maybe half a kilometer or 1 kilometer, and you can actually monitor continuously a particular site for a really, really long time, which is not possible on a UAV. But recently UAVs are also coming with a power line which can actually stay there up there, but mostly at only about 100 meters and so on, but not more than that. At the very best in the market itself. But then these things can stay up at 500 meters or 1 kilometer or even higher for days together and then monitor. So why I'm saying this is also that recently we had an inquiry about 6 months ago from the Raj Bhavan here asking if we can actually monitor mines with this mining activity as to where the mining equipment is moving around and how much they're carrying and so on, with an infrared sensor for the night and the daylight sensor during the day. So you can think of a large number of applications in such things. So that's more or less something from our side. So this actually works. So some of you want to see how its orientation works, so we can run the code and show you privately there somewhere. So thank you very much for the invitation, and I hope you got something from this.